This is problem solving session 7 for the course Introduction to Information Theory offered by NPTEL. I'm your TA Sachin from the EC department in the Indian Institute of Science. We will be solving problems based on multiple choice questions based on content covered in week 7 of the course, which contain the topics Gaussian channel, parallel Gaussian channel. Question 1. Consider a Gaussian channel with bandwidth 10 gigahertz if the transmit power of 2 watts is used and power spectral density of noise is 0.001 watt per hertz. What is the capacity of the channel? Is it A 1.44 kilobits per second, B 2.88 kbps, C 0.72 kbps, or D none of the above? We saw in the lecture that if the bandwidth is W, here W is 10 gigahertz, power constraint is power is 2 watts, and noise spectral density in 0 by 2 is 10 power minus 3 watts per hertz. Then we saw in lecture that the capacity of a band limited Gaussian channel is given by C is equal to W log of 1 plus P divided by N0W. Now we just need to plug in the values. 10 into 10 power 9 log of 1 plus 2 divided by 2 into 10 power minus 3 to 10 into 10 power 9. is 10 power 10 log 1 plus 10 power minus 7 and log of, so this is 1.0000001. This turns out to be 1.44 into 10 power minus 7. So this is 1.44 kilobits per second, which is option A. Question 2. The capacity of a Gaussian channel in bits per transmission with noise variance n without any power constraints is option A 0, option B half log of 1 plus p over n, where p is finite, infinity, none of the above. Solution. So when there is no power constraint, the capacity is limit as p tends to infinity, half log of 1 plus p power n. So as p tends to infinity, p over n tends to infinity. 1 plus p over n is close to p over n, and which is tending to infinity. So log of 1 plus p over n also tends to infinity. So this is infinity. So the capacity of a Gaussian channel with noise variance n without any power constraints is infinity. Question number 3. The capacity of a Gaussian channel with noise spectral density n0 by 2 equal to 10 power minus 3 watts per hertz. Power P is equal to 2 watts without any bandwidth constraint if option A 0 bits per second, option B 1.44 kilobits per second, option C is infinite, and option D is none of the above. From the lecture, we know that the capacity in bits per second of a Gaussian channel with infinite bandwidth power P and noise spectral density n0 by 2 is given by C is limit of W log of 1 plus P over n0 W. So can write this as log of 1 plus P over n0 W by 1 over W, as 1 over W tends to 0. Then this is in the 0 by 0 form because 1 over W tends to 0, so 1 plus P over n0 W tends to 1. Log of that is 0. And you can use the L'Hopital rule, differentiate numerator and denominator. Of course, before doing that, you can replace 1 over W by a different symbol, say x. So this limit will become limit x approaches 0 log of 1 plus P over n0 times x divided by x, and if you differentiate with respect to x, you will get, so it will be 1 over 1 plus P over n0 W into chain rule. So derivative of the thing inside, which is P over n0 W. Of course, this holds true only for natural logarithm. So you have to convert it to natural logarithm by multiplying by log e to the base 2. And denominator will be 1. So as 1 over W tends to 0, this becomes P over n0 log e to the base 2 bits per second. Now we have the value of P is 2 N0 by 2 is 10 power minus 3. So N0 is 2 into 10 power minus 3. Of course, you have to make sure that the units are consistent. Power is in watts and N0 over 2 spectral density is in watts per hertz. So P over N0 will be in hertz into bits per second. Um, so you will end up with C is 2 over 2 into 10 power minus 3 log e to the base 2 is 1.44. This is in bits per second. This is nothing but 1.44 kilobits per second, which is option B. Question 4. In a Gaussian channel, the received signal y is given as y is equal to x plus z, where signal x is distributed as a Gaussian distribution with expected value 0 and variance 4, and noise is distributed as normal distribution with mean 1 and variance 1. What is the capacity of this channel in bits per transmission? Is it 1.16, 0.76, 1.29, or none of the above? So we saw in the class that for a Gaussian channel, with power constraint E and noise variance N, the capacity is half log of log to the base 2, 2 pi E into E plus uh, 1 plus P over N bits per transmission. Now, in this question, n is noise variance is 1. They have not given you a power constraint. So, actually, I think you should consider the signal given. So, they're given a signal x distributed normally with mean 0 and variance 4. You should assume that this signal achieves capacity. So a Gaussian channel achieves capacity when the input distribution is also Gaussian with mean 0 and some variance. Varying if so, that will depend on the power constraint. The power constraint is P, then the input signal which has P as its variance, the normal and Gaussian distributed input signal, that will achieve capacity. So since they have not given anything here, then assuming X achieves capacity, um, the P here is the um, power constraint, which is the variance of the input signal, which is 4. So with this, the capacity is half log of 2 pi e into 1 plus 4 over 1, half log of 10 pi e, half log to the base 2 of 10 into 3.14 into 2.72. That should be uh, good enough. Rounding off 3.14 times 2.72 times 10 and log of that to base 2. Sorry, SO 2 pi e, my bad. SO 2 pi e, it's just half log of, or let me keep it as it is and write one more step instead. It's half log of p plus n minus half log 2 pi e n. That's because capacity is max of xy with the input power constraint T of x square less than or equal to p. This max of h of y minus h of y given x. But y is z plus x. So h of y given x is h of z plus x given x. But given x, there's no uncertainty in x. So there's only the uncertainty in z plus x is only from the variable z. So h of z plus x given x is h of z given x. But z is independent of x. So this becomes h of y minus h of z. And Um, this z is independent of x, so it does not depend on the input distribution, max overall input distribution. So h of z is half log of 2 pi en, this term. Now to maximize y, h of y, the distribution that maximizes that is a Gaussian distribution which has variance p. So in that case, y is the sum of two Gaussian distributions. One of them has variance n, mean 0, and the other has variance p and mean 0. So that itself, the sum of two Gaussian distributions itself will be a Gaussian distribution with mean 0 and variance p plus n. So the differential entropy of that will be half log of 2 pi e into p plus n. So the variance of the sum distribution is sum of the individual variances. So the capacity becomes half log of 2 pi e into p plus n minus half log of 2 pi e n. And then you can take the half common, you get log of a minus log of b form, which is nothing but log of a by b. So it's log of 2 pi e into p plus n divided by 2 pi e into n. So the 2 pi e's cancel each other. You're left with half log of 1 plus p over n. So now don't have the 2 pi e here. You're left with 1 plus 4 over 1, which is 5. And what is log 5 base 2? It's 2.31, 2.32. So this is 1.16, which is option A. So that is fourth question. Question 5. So let us consider three independent. Huh? No, the mean of the noise doesn't matter. No. Let Yeah, I don't think the mean changes the entropy. I'll have to go back and see the derivation, if they have used the mean or not. As far as I know, it shouldn't matter. I don't think it changes. No, the mean doesn't change the entropy for Gaussian random variables. It only depends on the variance. I'll be back. I need to go to the washroom once. Be back in 5 minutes. I'm back. So, if you do the derivation for differential entropy of a Gaussian random variable with mean mu instead of 0 and sigma square, and h of x is minus integral the density log of the density function. If you carry out the integration, if mean is 0, what you get is e of x square by 2 sigma square plus half log of 2 pi sigma square. So instead of mean 0, if you have mean mu, you'll end up with half expected value of x minus mu whole square divided by 2 sigma square. And e of x minus mu whole square is the variance. So this is equal to sigma square by 2 sigma square plus half log 2 pi sigma square. So this is just again half plus half log of 2 pi sigma square. Or you could write this as log e and take it inside the other log. So you'll be left with 2 pi sigma square e. So changing the mean doesn't change the entropy, differential entropy. Coming to the next question, let us consider three independent Gaussian channels in parallel with a total power constraint of 2.5 watts. The noise power of these channels are given by N1, N2, N3 equals 1, 2, 3 in watts. What is the optimal power allocation P1, P2, P3? And the options are 1 by 6, 2 by 3, 0 in watts, 2, 0.50. Option C is 1.75, 0.75, 0. Option D is none of the above. The solution here is, so we allocate power uh, optimally by using the water filling method. By that, what I mean is, let's say you have the channels on this axis and power here. We have three channels. Uh, the noise in the first channel is 1, noise in the second channel is 2, and noise in the third channel is 3. So imagine you have a container in which you have placed blocks in this way. Now you have to pour water into this. What happens is the water will always settle at some height like this, which will be equal across, right? If you pour water into this, into a container like that, or it could be like this, all of this is water. So the level of the water will be fixed, will be the same across all three blocks. The same is the case when you try to optimize the power allocation. So you can, this is channel 1, this is channel 2, and this is channel 3. This is N1, this level is N2, this level is N3. So now you have 2.5 watts that you have to share among these three. Then now you have to pick, suppose the power level, suppose your water is at this point for some value V, then you find the height in the first channel, height of the water relative to the noise, the second channel, and relative to the third channel, like this. So if this is at level V, then the power that you need to allocate to the first channel is V minus N1. Power that you allocate to the second channel is V minus N2. Power that you allocate to the third channel is V minus N3. And the sum of all the powers that you have allocated should be 2.5 because your total power constraint is 2.5. So this will imply 3V minus N1 is 1, N2 is 2, N3 is 3 is 2.5, which will imply V. You can solve this, you'll get V is 2.5 plus 6 by 3, 8.5 by 3, which is 2.83. Now, if you do allocation according to this, then 2.83 minus N1 is 1.83. 2.83 minus N2 is 2.83 minus 2, which is 0.83. 2.83 minus N3 is 2.83 minus 3, which is minus 0.17. But you can't allocate negative power to any of the channels. Worst you can do is you can skip, you can just not allocate any power to a channel and just leave it. You can't really allocate negative power. So the power allocated to a channel I is V minus Ni plus. That means if that quantity V minus Ni is positive, you allocate that much. If it's a negative quantity, you allocate zero. So in this case, V minus N3 less than zero, so do not allocate any power to channel 3. I'll finish the solution to this question and then you can ask your question. So now in this picture you're not allocating any power to channel 3. So what happens is uh, there's no power above the third channel. So the water or power is sitting at some point here. That's it. You are allocating this much to channel 1 and this much to channel 2. Nothing is being allocated to channel 3. So this is your new V. Now again to satisfy the power constraints, V minus N1 plus V minus N2 should be equal to 2.5 ohms, which means V is 2.5 N1 plus N1, which is 1 plus N2, which is 2 divided by 2, is 3.75. Now what is it? 5.5 by 2, which is 2.7. Now what is the allocated power? P1 is V minus N1, so 1.75. P2 is V minus N2, which is 2.75 minus 2, which is 0.75. P3 is actually plus here, E minus N3 plus, which is 3 minus 2.75 minus 3, which is minus 0.25 plus. So since it's a negative quantity, the plus will make it to 0. So the right answer is 1.75, 0.75, 0. Alright, somebody had a question? Yeah. Uh, Actually, I don't know because I have not written the exam and I don't set the question paper. So I'm not from the IIT where this course is being offered. Like, I'm only here for the problem solving sessions. So what you can do is, in your course page, have you checked there's a section called Q&A? In, no, that Q&A there, if you go there, it'll lead you to a Google group, right? Uh, uh, Actually, I don't have direct contact with the course instructor. Yeah, so he has his own TAs because all the material is prepared and maintained. All this exam is done by the original course instructor, Professor Adrish, and his TAs from IIT Kharagpur. Right? Yeah, oh, it shouldn't be. I don't think it should be that hard as long as you remember the formulas. It should be fine. Oh, I don't think they will ask IIT level questions. They won't set the paper to the level of the IIT. I don't think so. Yeah, because they have to evaluate people from all over the country, right? So they can't set the standard so high. Then a lot of people won't be able to score really well. No, no, no. They will set it so that you should be able to solve within the allotted time. Usually, whenever they set an exam, they will solve it themselves. And the TAs, sometimes they take the help of TAs to set the papers. So the TAs themselves should also be able to solve. And the TAs who haven't worked in the same lab, uh, who haven't set the questions, even they should be able to solve. They will time it. At least that's what they do in IIC. So they will time it such that the TAs can do it within one third of the time that a student is expected to do it within. But the NPTEL specific, I don't know. It's all right because even Professor Adrish, I don't really have direct contact with him. Only sometimes, maybe during PMRF evaluation or something, I will talk to him. But yeah, if you put it in the Google group, maybe he hasn't seen it. Maybe he's busy. You can ask again and see if someone answers. Okay. Question 6. What is the capacity of the Gaussian channel described in Q5? 1.31 bits per transmission, 1.38, 0.96, or is it none of the above? Solution is for Parallel Gaussian channels, the capacity is the sum, uh, C is sum of half log 1 plus pi over ni for all I, where pi is the power that you allocate. Uh, the optimal power allocation that we just saw in the previous question, and Ni is the noise in the ith channel. So since we allocated zero power to the third channel in the previous question, P3 is zero, so half log of 1 plus 0 is half log 1, which is 0. There are only two terms here. First term is half log of, it's 1 plus P1 over N1, half log of second term is P2 over N2, and P1 over N1 is 1.75 divided by 1. P2 over N2 is 0.75 divided by 2. This half log of 2.75 plus half log of 1.375. This is 1.46 divided by 2 plus, let me see, log of 1.375 to the base 2. Point 0.46 divided by 2, which is 0.73 plus 0.23 is 0.96. So option C. Question 7. Let us consider two correlated channels, Gaussian channels, with output yj equals xj plus zj. J belongs to 1 to 2. The input x is distributed as normal distribution with covariance matrix kx means 0. Noise z is distributed as the matrix is 1 0.5.51 for an average power constraint of 1 watt. What will be the optimal value of matrix A is equal to Q transpose Kx Q, which achieves capacity. Options are 1.5, 0, 0, 0.5, 0, 0.5, 1.5, 0. C is 0.5, 0, 0, 1.5. D is none of the above. So this was done in class, except that there were no specific numbers given, only the general derivation was given. So you have to maximize the determinant of kx plus kz given the trace of kx must be less than or equal to np, which implies we have to maximize the determinant of a plus lambda given the trace of a is less than or equal to np, n is 2 and p is 1 in this question. So the trace of A, it's a 2 by 2 matrix, so the trace is A11, the entry in the first row, first column, plus A22 less than or equal to 2. The maximum value, so all this you was done in the lecture, so exactly how this came about, if you want to know, you have to go back and see the recorded video. And maximum value is attained. The other constraint we have is aii plus lambda is equal to v. So a11 plus lambda 1 equals v, and a22 plus lambda 2 equals v. Again, this aii is v minus lambda I, but in fact it's v minus lambda I plus. So if it's a negative quantity, we set it to 0. Now to lambdas are the eigenvalues of the matrix kz, and we need to find q and q and q transpose. That also comes with the singular value decomposition of kz. Kz is 1/2 We have to do SVD, singular value decomposition. You will get minus 1 over root 2, minus 1 over root 2, minus 1 over root 2, 1 over root 2. So 1.5, 0, 0, 0.5, minus 1 over root 2, minus 1 over root 2, minus 1 over root 2, and 1 over root 2. This is the matrix Q. This is your capital lambda. This entry is lambda 1. This entry is lambda 2. This is the matrix transpose of Q. Here, in this case, it's equal to Q. So to find the eigenvalues, you have to solve kz minus lambda I, determinant is 0. So 1 minus lambda half, half 1 minus lambda. 1 minus lambda square minus 1 over 4 is 0. 1 minus lambda square is quarter. 1 minus lambda is, right? Or did I make a mistake somewhere? So this is a plus or minus half. So if 1 minus lambda equals half or 1 minus lambda 1, there are two roots. 1 minus lambda 2 is minus half. So lambda 1 is half, lambda 2 is 3 over to 1.5. Or you can write it either way. Okay, I'll consider the half value as my the larger value as my lambda 1 and the smaller value is lambda 2. Lambda 1 is 3 over 2, lambda 2 is half. Finding Q and Q transpose, I'll leave that to you. I won't go into that, but you can verify that this is the singular value decomposition. This is an aside. So once we have that, we have A11 plus lambda 1 is 1.5 is equal to A22 plus lambda 2 half. So A11 minus A22 is, or A22 minus A11 is 1, and we also had A22 plus A11 less than or equal to 2. So we maximize, um, we have to maximize the determinant of A plus lambda, uh, which is equal to the product of, which is less than or equal to the product of AI plus lambda I. So we also have to maximize this AI plus lambda I. So we have to have as large of a, so this lambda I is dependent on noise, we can't control that. So you have to maximize this. AII value also. So best we can do is equal to 2. So I'll take that as 2. Then what you get is A22. You add these two equations. You get 2. A22 is 3 or A22 is 1.5. And you subtract the two equations, then you get 2. A11 is 1. A11 is 0.5. Then A is Q transpose KXQ. So we have the diagonal elements, um, 1.5 and 0.5, which is option A. Sorry, A11 was 0.5, A22 was 1.5, which means it's option C. So the why we need to optimize determinant of kx plus kz, and why optimizing that means optimizing a plus lambda. So why maximizing a plus lambda means we have to maximize ai plus lambda I and set them equal to the same quantity v for all I. These 3 points you have to go and check in the lecture. Question 8. What will be the channel capacity in bits per transmission of the channel described in question 7? Options are 5.5, 5.1, 3.9, 1.2. So now we found A that maximizes A which achieves capacity. From that we have A is Q transpose KXQ. So KX is QA transpose, which will be equal to 1 minus 0.5 minus 0.51, and then the capacity will be given by h of y1 y2 minus h of z1 z2, which is half log to the base 2 of 2 pi e squared determinant of ky minus half log of 2 pi e squared determinant of kz. But ky is x plus kz, so this becomes half log of, we can also take uh, half common and then you will get log a minus log b, which is log of a by b form. So this is half log of determinant of kx plus kz. The 2 pi whole squares cancel each other by determinant of kz. Kz is this matrix. Kx is ky is kz plus kx, so it is 2002. Determinant of ky is 4. Determinant of kz is 1 minus 1 over 4, 3 over 4. So c is half log to the base 2 of 4 divided by 3 over 4. Half log to the base 2 of 16 over 3, which is log 16 minus log 3. Log 16 to the base 2 is 4. So 4 minus log 3 to the base 2, which is 1.2 bits per transmission. That's option D. Question 9. Consider a cascade of two Gaussian channels. Y1 is x plus z1, y2 is y1 plus z, y1 plus z2 with a power constraint P on x, and z1 is distributed in mean 0 variance sigma 1 square. Z2 is Gaussian distribution with mean 0 variance sigma 2 square, and z1 z2 are independent. Find the capacity of the channel for IXY1. Options are infinity, half log of 1 plus P over sigma 2 square, half log of 1 plus P plus sigma 2 square, sigma 1 square. Option D is half log of 1 plus P over sigma 1 square. And solution is straightforward. IXY1 standard case of Gaussian channel with noise variance sigma 1 square and power constraint E. So the capacity is just half log of 1 plus P over sigma 1 square. Question 10 is a little different, and it says for the Gaussian channel given in Q9, find IXY2. So in this case, first you have one channel which adds noise N1, and after that, after adding noise N1, you pass it on to the next channel which adds noise N2. Since it's additive Gaussian noise, so equivalent Z1 plus Z2 is also Gaussian. So this is equivalent to a channel with input X, noise Z1 plus Z2 distributed according to, since mean is 0, variance are added up, and Y, the output is X plus, first you add Z1 and then you add Z2 to that. Hence the capacity C is half log of 1 plus P over N, which is half log of 1 plus P over sigma 1 square plus sigma 2 square, which is option B. With that, we are done with week 7. I will see you next week for problem solving session number 8.